Hello, my name is Jia Xue. I'm from UMAT Materials, Natural Resources, Canada. The topic of my presentation today is finite element analysis to investigate the effect of loading modes on the CTOA of DWTT specimens. The outline of this presentation will have 4 sections. In section 1, we will have a brief introduction about the background of CTOA, which is short for crack tip opening angle. The major question we want to answer in this presentation is CTOA a material constant or it is actually dependent on loading modes? In section 2, we will have a description of the finite element model we used in this research. We will discuss the material properties. We will discuss the damage mechanics model we used to simulate crack propagation, and we will discuss the mesh size and boundary conditions. In the section 3, we will discuss the crack profiles, compare with simulation results to test results. And then we will discuss the measurement of CTOA in simulations. And then we will discuss the CTOA distribution across thickness at various distance behind the crack tip and comparing the bending mode and the tension mode. And in section 4, we will have conclusions and future work. In this research, we find that the CTOA predicted by FEA is actually in agreement with experimental data, and the CTOA is quite consistent in the tension and bending mode. Crack tip opening angle CTOA has been proposed as a material parameter for control of fast ductile fracture propagation and arrest of axial cracks in gas pipelines. In a real case scenario, when a gas pipeline fracture, the crack can run hundreds of meters. And it will be very expensive to try to repeat that process by doing a large-scale pipe test. And on the other hand, we can do smaller lab tests, such as this drop weight tear test. And the measurement of CTOA using DWTT specimen can be found in the STM standard E3039. Which will be very cost-effective compared to the large-scale pipe test. And besides this test, we can also do finite element analysis to investigate CTOA. And the objective of this research is to investigate the effect of loading modes, such as bending and tension on CTOA. The first thing we talk about our finite element model is material property. In this research, we used X80 pipeline steel, and it is assumed as isotropic and elastoplastic. And to simulate crack propagation, we use damage mechanics model, in this case MMC model. The strain to initiate fracture, which depends on stress triaxicity and the load angle. So instead of one constant value, we used a surface. And this surface is dependent on stress triaxicity and load angle. After damage initiation, the softening of the material is controlled by the damage evolution. And we are using exponential damage evolution law here. And this figure shows a curve of a stress-strain curve of a single element under uniaxial tension. And we can see here in the beginning, the material is elastic, and then it goes plastic, and then it goes damage. And the damage starts from 0, and if we continue to increase the strain, the damage will increase to 1. And that means the element has been fully damaged and will be removed from the mesh. In this research, we want to investigate the effect of 2 different loading modes. So we have 2 models with different boundary conditions. On the left-hand side, you will see the model of 3-point bending. And on the right-hand side, you will see the model for the uniaxial tension. And in both models, we use 1/4 symmetric boundary conditions. And in both models, we use very fine 0.5 millimeter mesh at the crack path. And in other part of the model, we use coarse mesh, which is 2 millimeters. And we use this tie constraint in Abagus to connect the coarse mesh to the fine mesh. Here is the beginning of section 3. We will discuss the simulation results. And this slide will show a video of the crack propagation of the drop weight tear test specimen under 3-point bending. And we can see that the crack is turning. This slide here shows crack propagation of drop weight tear test specimen under uniaxial tension. As we can see here, the crack propagation is turning and is flat fracture. And we would like to mention that our model can also simulate slant fracture. But for current work, we only discuss the flat fracture here. This slide shows the crack profiles predicted by the finite element analysis. And on the top, we have this crack profile from the tension mode. And in the middle, we have the crack profile from the bending model. And in the bottom, it is a crack profile from the interrupted bending test sample. And as you can see from here, the crack profile is quite similar here. Here we discuss the measurement of CTOA in Abagus simulations. As we know that CTOA is the crack tip opening angle, which is determined by the crack tip opening displacement, COD, at a fixed distance behind the crack tip. And we developed this Python code, which will locate the crack tip and output the COD, crack tip opening displacement, and then we can calculate CTOA from that. This slide here shows the CTOA as the function of crack extension. We have 4 curves which are from the FEA prediction, and all the red curves are from the bending model, and the blue curves are from the tension model. And by CTOA surface, it means that the CTOA is measured on the surface of the specimen, and the CTOA middle means that the CTOA is measured in the midsection of the specimen. And we can see from the figure here, in the beginning of crack propagation, the CTOA is quite high. And after 20 millimeters of crack propagation, the CTOA becomes stable up to 40 millimeters of crack propagation. And in that region, in that steady region, the CTOA predicted from the FEA is quite similar to the CTOA from the test result, which is the black curve here. And of all these curves, we see that this red dot curve, which is the CTOA under bending at the surface, this curve is higher than all the other curves. This slide shows the CTOA distribution as a function of crack extension at 4 different distances behind crack tips. All these 4 curves are measured from the bending mode, and the CTOA is measured in the mid-thickness of the specimen. And these all curves are ranging from 0.5 millimeter behind crack tip up to 7 millimeter behind crack tip. And we can see from here, all these 4 curves are showing similar trend. And there is no major differences between 0.5 millimeter up to 3 millimeter behind the crack tip. And the CTOA only increase slightly at 7 millimeters from crack tip, and 7 millimeter is about half the thickness of the specimen. This slide shows the CTOA distribution as a function of distance behind the crack tip at crack extension of 30 millimeters for both bending and tension model. And all the red curves are from the bending model, and all the blue curves are from the tension model. For the tension model, CTOA is almost the same on the surface and in the interior up to 10 millimeters behind the crack tip. And at distances larger than 10 millimeters, the CTOA on the surface becomes larger than that in the interior. While for the bending model, the CTOA measured on the surface is always higher than the CTOA measured in the interior. This slide shows the CTOA distribution across the specimen thickness at crack extension of 30 millimeters. And the thickness of the model initially is 30.7 millimeter, but it becomes thinner as the crack propagation, and the thickness after deformation is about 10 millimeters. As we see from this figure, the CTOA for the tension model shows no obvious variation through the thickness, while the CTOA for the bending model shows an increase of CTOA from the mid-thickness to the surface. From this research, we can draw the following conclusions. First, in this research, we used a state-dependent damage mechanics model to investigate CTOA. The CTOA predicted with the finite element analysis agrees well with the experimental data. Secondly, the CTOA distribution behind the crack tip is found to be consistent up to half the thickness distance behind the crack tip. And at a distance larger than half the thickness, the CTOA starts to increase gradually. Third, for the bending model, the CTOA on the surface is higher than that in the interior, which is in agreement with the experiment. And for the tension model, there is no significant differences between CTOA measured on the surface and CTOA measured in the interior. And fourth, the CTOA is consistent in both bending and tension model, and both cases show that there is a steady state propagation. And finally, the results from this research support the use of a constant CTOA measured using drop weight tilt test specimen and ASTM standard E3039 to other geometries under a range of loading conditions. And for the future work, we will focus on the investigation of more complex stress state, such as the biaxial stress state. Thank you for your attention, and please let me know if you have any questions and comments. Thank you.